So, welcome back to one more lecture on introduction to soft matter. Last time we were discussing the solutions to the cases of the 3 parameter model and its different solutions. One of the things that I would just like to point out before I start today's class is that the last expression that we wrote, and this is the expression of the Laplace when we took the Laplace inverse. We got expressions in the time domain. Now, see this, I am using a variable s here also, but this is just so that I am consistent with what I have done before, and this is just a this s here represents a dummy variable for the integration. You can replace it with any other, you can replace it with a tau, you can replace it with any other variable you want, and the expression will still remain the same. So, this s here in the time domain should not be confused with the s of the Laplacian function. So, what we want to now do is we want to look at one more model, okay. And so let us take a look at we had done one. So, when we had started off, so the 3 parameter models. So, we had in the beginning we introduced 2 different 3 parameter models and we solved for this particular case. So, let us now solve for the other one, okay. So, I am just going to redraw this. Okay, so the model looks like this, right. So, now let us say this is E, this is my dashpot characterized by eta, this is my another spring which is E1, okay. And here, so the obvious question one needs to ask before we even try to solve this is, will this have a solid like behavior or a fluid like behavior, right. Now, this is a Kelvin Voigt model, right. So, we have put a Kelvin Voigt in series with another spring, right, and that is what it is. So, the Kelvin Voigt we know already has a solid like response, because for a finite force the displacement of the system is already bounded, is going to be finite, and the same holds true for the spring. So, even when you put these two together, where for a finite force the displacement in both of them are going to be bounded. So, this represents a solid model. So, this is appropriate for a viscoelastic solid, okay. So, this is so, this is a Kelvin Voigt Mayer model. So, or sorry, I forgot Mayer, but okay. So, when you say Kelvin Voigt, you know Mayer's name should also be there, okay. So, now let us recall what was the governing equation for the Kelvin Voigt model. So, just we will quickly go back, scroll back to where we are discussing the Kelvin Voigt, and we had gotten this particular expression, right. So, now just like the previous case where we had introduced the operator D, I can write this as that for the part of the Kelvin Voigt, this expression holds true. Kelvin Mayer, okay. So, now let us analyze this in the system such that, let us say the displacement that is seen by the first body is going to be delta x kV, and that the force it experiences kV, function of time. The spring on the other hand is going to see an extension of delta x s, and a force of Fs. Now, these two, so I am treating the, so I am going to treat this entire thing here as one system. So, now I am just going to write the force balance. So, for force balance, so from force balance, and remember these are all massless quantities, right, the springs, the dashpots are all massless. So, now I am going to apply the force balance once again, and in this particular case, in the case of the series system, you will see that the forces are all the same. And then from geometry, we get a different relationship for the displacements, right, and that replacement is delta x is equal to so the entire system displacement is given by the sum of the individual displacements, and the relationships that we have are, so also given the individual constitutive relationships, you have that the force in the spring is equal to, is the same as the force in the system, is equal to E1 times delta x s. And in the Kelvin-Voigt body, you have the force, if I want to write that, this is again equal to the entire force experienced by the system, and now this is equal to eta times d plus E times delta x kV. Now, please remember that this d is the differential operator, so it is a ddt here. Okay. So, I want a relationship between F here, the left hand side in the force balance equation, and the delta x, which is again on the left hand side of the geometric relationship, right. So, ideally I would be able to get delta x simply by adding these two. So, add these two. Now, I do not want to take this into the denominator, because this is actually a differential operator. Okay. So, what I want to do rather is I want to be able to keep it in the numerator itself and then add this up. To do that, there is something very simple we can do, which is we introduce another multiplicand. So, I am just going to erase this, because I just want to keep the right order. So, we can multiply both sides, or actually let me leave it like that. So, to add this, what we are going to do is we are going to multiply. So, I am going to rewrite times of f t equal to, rewriting the first expression E1 delta x s, and in the second one, for the second equation here, I multiplied that with E1. So, if I multiply E1, this is still f t, and we have E1 times d plus E delta x kV. So, now this is in a form such that you can simply add these two expressions. So, you just add, and what you end up with is eta d plus E times of f t plus E1 f t, and when you add these two together, then it has the same constant, the delta x s and delta x k v have the same constants. So, that just comes outside delta x, right. So, if I were to use this operator, then we end up having, so this is the same as writing f eta times f dot t plus E plus E1 of f t that is equal to E1 eta delta x dot plus so now this suggests this suggests this is now the relationship between the force and the displacement. So this will suggest this suggests a constitutive equation of the form right, and this is the answer I was looking for. Now, the important thing I want you to note here is that this is again a linear ODE, and the linear ODE has the derivative of stress, the stress itself on the left hand side, and on the right hand side you again have a derivative of the strain and the strain itself. And this is exactly in the same form that we had the other expression. So, this again can now be written as, so given this form, one can again write it, again rewrite this expression, this as being P1 sigma naught sigma dot plus P naught sigma equal to Q1 epsilon dot plus Q naught epsilon. The only difference now is that the values of the coefficients are changed. So, I have to now specify what the values are. So, this value will be P1 equal to eta, your P0 is E1 E plus E1, Q1 is equal to eta E1 and Q0 is E1. So, now you probably can now appreciate why we were solving the entire thing in the form of these coefficients previously, because when we are solving this, so I am just going to quickly go back to the old solution. So, we are trying to solve this particular expression in the previous case, and when we did the Laplace, there is nothing here which assumes anything about the model itself. The model builds in the way that the values of P1, P naught etc. are set. So, to now get the solution of this particular model, all you need to do is to insert the values of the P1, the constants in the solution. So, the solution for the stress relaxation remains the same, and so does this expression remains the same. Almost all the expressions actually remain the same. Okay. This one quick thing, and that is, remember that for this model to be physically realistic, when we had derived the stress function, the stress relaxation, then we had here a constant term, and then we had this other term in the bracket which was multiplied by an exponentially decaying term. Now, for this to be physically realistic, this particular fraction has to be greater than 1, greater than 0 for it to make sense, right, physically realistic system. So, we had insisted that Q1 by P1 minus Q naught by P naught should be greater than 0, which it was true for this particular case, because we saw that. So, we evaluated Q1 by P1 minus Q naught by P naught, okay, and we got we saw that this expression is actually equal to E and it is greater than 0. So, let us just do that here one more time. So, let us just ensure that this is a physically realistic model and you will get solutions that are going to be realistic. So, let us check whether Q1 minus P1 minus Q naught by P naught is greater than 0. Okay. So, now Q1 by P1 minus Q naught by P naught is equal to, you have eta E1 by eta minus Q naught, this is E1 divided by P naught, which is E plus E1. So, this is equal to E1 1 minus, so 1 minus E by this one, which is so this quantity here. So, this is a fraction which is, so here, okay. So, just a second. Okay. So, this quantity is now E1 minus E1 multiplied by a fraction, right, and this fraction is less than 1, because this is, if you look at the functional form of the numerator denominator, then this is less than 1. So, this quantity is greater than 0. Right. So, in a sense we are saved, we do not have to worry. Our functional form is such that that the physically realistic angle is retained. So, this particular system has the solution, and that same solutions that you have seen before can be applied in this case. Okay. Okay. So, we have done two 3 parameter models, right, and both of which we saw are actually good for representing the case of viscoelastic solids. Right. Now, it should be obvious to you that when we are doing the 3 parameter models, that there will be one more obvious 3 parameter model where you would not have a spring, but you would have a dashpot. Right. So, this model is also called, what we are going to introduce now is also called the Jeffreys fluid. Okay. So, the Jeffreys model. So, in the Jeffreys model, what you have is you have a Kelvin-Voigt system. So, you have an E, this is eta, and I am just going to say that this is eta and that is eta 1 in the same spirit that I have been. Okay. So, we are going to solve for this, but before we do that, we should ask ourselves one more time as an intuitive idea whether this is going to be viscoelastic, appropriate for a viscoelastic solid or a viscoelastic liquid. Now, take a look at this particular system. This is obviously the Kelvin-Voigt-Mayer body right here, right. So, when you apply a particular force, the displacement in this is going to be bounded. Okay. And but for the case of the dashpot, you cannot ensure that. So, even for small finite forces, the dashpot will keep on increasing or keep on displacing. So, this entire model will have a system level displacement, where the displacement will keep on occurring even for small forces, right, and that is reminiscent of a solid, for a fluid, right. So, this particular Jeffreys model is appropriate for viscoelastic fluids, and that is why this is also often known as Jeffreys fluid. So, this model is appropriate for a viscoelastic fluid, and hence, as I said, it is also known as Jeffreys fluid. Okay. So, we have the Kelvin-Voigt model once again. So, we are just going to borrow from last time what we had written. We had said here, we are just going to reuse this one more time. So, eta d plus E epsilon. So, for you have eta d plus E times the force is equal to, sorry, this displacement in this is equal to force, right. So, I am just reusing the expression from there. For the dashpot, so we are just using the same methods, right. So, you understand that when I say delta x kV, then that means that the displacement in the Kelvin-Voigt body, right. So, none of that has changed. So, when I am using that, you can understand that this force again is the force in this particular subsystem. Okay. So, for the dashpot, you again now have F d equal to eta 1 delta x dot d, right. And now we have to figure out what are the relationships between the different quantities. So, from force balance, now this system is actually exactly equivalent to the previous case, right. So, what we had written, the expressions that we had discussed for the other 3 parameter model are actually going to be valid even in this case. So, for the force parameter, just for the force balance, we can just use the previous particular case, and we can just say that the force in the system is going to be equal to the 2 individual forces, right. And from geometry, we are once again going to have the same expression, which was that the net displacement is equal to delta x kV plus delta x d. Okay. So, now where do we want to get to? We want to a relationship between the force and this displacement right here, right. The left hand sides of the two the force balance, and from the geometry the two relationships that we have. Okay. So, let us write down the expressions. So, now we have F t which kV, which is the same as the net force, is equal to E times delta x kV, and in this case I am just going to use this style. Okay. So, this is the expression for the first case, and for the second case we have force in the dashpot is again equivalent to the system force, because we have seen that, and that is equal to now eta 1 delta x dot, right. And now we want to add these two. expressions, right. So, that is what we want to do, and we cannot add these two up easily, because you have different. You can add. Okay. So, at this point what we have to do is that we have to simplify, or we have to do the addition in such a way that we can add all these up and we can get the net force on one side and we can get the net displacement on the other side, right. So, this is something that I would leave you to do for the next class, and then I am going to do I am going to solve it for you in the next class for you. Okay. So, we will stop here today, and what we have done is we have looked at another 3 parameter model, and we discovered that the solution for that is interesting the same as the solution for the previous case, except now that the coefficients are something that are just going to be determined by the particular model. And we are going to see that the same is going to be true for the Jeffreys case, and we are in the process of solving for that. Okay. So, next class we will complete the solution for the Jeffreys fluid.